So we have calculations and ways to actually calculate entropy, just like we have ways to calculate enthalpy. And there are these long charts. You're going to see this coming up very soon. But we can also get information just by predicting things about entropy. And ultimately, I want to let you know where this is headed is it comes to predicting whether or not a reaction or situation basically is spontaneous, meaning if it wants to go under the conditions you have it sitting there in. And so entropy and enthalpy together let us know whether or not something will just spontaneously happen or not. So we've got to study entropy a little bit more, and then we'll look into the whole picture of spontaneity. So one way that we can just make a general prediction about the sign of entropy is by looking about changing phases. So if you have something that's a solid and you're heating it up, you are increasing the entropy of it. Because if you are increasing the temperature, you're going to be increasing the motion of the molecules, and so you're going to change the phase of it. So this is due to temperature, and this is also due to spacing between intermolecular forces being further apart, and so those aren't holding things as tightly. So you can imagine that screenshot in your head again, and if you keep taking screenshots of these atoms being in all different places every time you screenshot it, whereas these are just in slightly different vibrated positions. So as you go from a solid to a liquid, that does mean that you have an increasing entropy. And then as you go from a liquid to a gas, you have even more of it. So that's one scenario. If you are just changing phases, you've got the same substance. Solid to liquid increases entropy, that's a positive entropy term. Liquid to gas increases entropy, that's a positive entropy term. Now let's take it just a little bit further. What if you have a solid and you dissolve it in water? And at the moment, we aren't going to even be looking at how much entropy the water itself would add to the system. But if we just look at the NaCl atoms, right here, there are two reasons that entropy is increasing here. In the one situation, you can think, well, I've got a block or this little pair of these NaCl, so it's one on this side, and I'm making two on this side, and the two that I'm making are more mobile. So my screenshots are going to look more and more different. My predictability is going to be more and more different, so I am going to have an increasing in entropy. Secondly, though, is that again, and it's related to those, it's tied together, but it's related that those chlorine and sodiums, now that they're dissolved, they do have that increased mobility and the attraction to the water, and so they can move about freely. There's more motion involved, and so because it's in that liquid medium, and so that also is the reason. It's also the phase that it's been moved into. Not just that there are two, but also because of the phase. So both of those are factors. If you are making more of something, then that can increase entropy, or just dissolving something is going to increase entropy because the increased mobility also. Now here's another one. If you're looking at a reaction, and you might find this interesting, you're going to have to ignore my bottom picture here because I've got one thing after this. So if you are looking at a reaction, if we take sodium bicarbonate and we add some acid to it, well, you probably know this if you've ever made a sodium baking soda volcano. What happens is you create CO2 gas. You probably never noticed that you made a little water along the way. And you probably didn't notice that you made NaCl because it's an ion that's soluble in water, so it would have dissolved in the water you had everything in. But that is what happens. And so if you look at this, first of all, we are starting with 3 things on the left and we are making 4 things on the right. But you can't really just make a decision based on how many there are. You only would make that kind of decision if everything was the same phase. So if absolutely everything was alkylbase and you couldn't figure anything else out, if you have 2 on the left and 4 on the right, then that would be some increase in entropy. But there is a better way to see the entropy, and it is literally seeing it. Notice on the left side, we have something all nice, stacked nice and neat, and then we've got something in water, and you can see how it's like all moving all about. But on the right-hand side, we are creating something that has a lot of entropy. We already know gases have a lot of entropy. We also, we have a match on the liquid. We have 2 matches on the liquid, but then we also have the NaCl. It's dissolved in with those NaCls on there. And so we actually are increasing a little bit more of the aqueous phase. But what I will say is that an increase in any reaction that will produce gas, that is a huge increase in entropy. So if on the left side you don't have any gases, and on the right side you have 1 gas, then that's an increase in entropy. If you had, on the left side, if you had 3 gases, and then if you had 5 on the right-hand side, now gases, like I said, this is a huge increase in entropy. That would for sure mean that the right-hand side has a lot more entropy. But you can't just necessarily say, oh, well, I've got a solid, 3 gases, and, 6 liquids, and then because I have 5 gases, this isn't decreasing entropy. The phase trumps it. So the fact that there was making that gas, that's what gives us that entropy of the system. So this is a good reaction example to show you something that's creating a lot of entropy just visually. And then finally, if we just had you compare atoms or molecules, again, if you go back to the molecule, just straight the atom level, the atomic level, and you're looking at the electrons, we've already talked about how electrons can bunch up and group, and you don't keep them the way they're drawn here. So if you take one screenshot, that one electron, it might be right there, but then another screenshot, the electron might be there, and then another screenshot, it might be there, right? But he's kind of in that space. Remember, this isn't really the picture of the atom. It's really talking about the electron can actually move all around the surface right in there on that first energy level. But I'm just saying that there's just one electron doing that. Over on the right-hand side, so if we just moved one, you could have one there. You could have it's over there. You could have it over here. But then imagine all of them are all moving at the same time. So every screenshot for every one of these being in slightly different locations. And you can see how the more electrons that you have in something, if you're just comparing, atoms or molecules, the more electrons something has, the more chaos it in and of itself, of its nature, it's going to have. So that is going to walk you through. You've got some examples coming up to practice this and to see what's going on with your entropy and what's helping you make some entropy predictions. Remember, entropy might be a little counterintuitive. The more entropy you have, the higher the positive number. If you would like using disorder to describe entropy, sometimes this can throw people off a little bit. Disorder, when you have more a lot of people will think negative because they're thinking disorder and order. More disorder is a positive term. Negative S would be more order. So if you like using that terminology, just be careful in how you're thinking of it. If you're using entropy and just think of it being like chaos or movement or probability predictions being difficult, then that would be increased entropy, and that'd be positive.